this morning lecture by Professor Pambuccian. This will be the last lecture before the Easter holidays. So today we will talk about reverse geometry, and I remind everybody that the next lecture will be the 28th of April at 11 o'clock. Thank you.
So the subject of today's lecture has a long history, but a history that has been somewhat lost or is in disrepute today. So I'll start with a little bit of motivation for it. The earliest we can find this kind of a reverse enterprise is in Pappus. I have to say that it is debated, hotly debated, what Pappus meant by analysis and synthesis. But in one interpretation, it has some reverse meaning. So, what does he say? He says that analysis is the path from what one is seeking, as if it were established by way of its consequences, to something that is established by synthesis. That is to say, in analysis, we assume what is sought as if it has been achieved, and looked for the thing from which it follows, and again, what comes before that, until by regressing in this way, we come upon some one of the things that are already known, or that occupy the rank of first principle. We call this kind of method analysis, as if to say reduction backward. So as you see from this quote, it seems pretty clear that it goes in a reverse direction, that you start with a known result and you look for first principles from which it follows. As I say, the literature about this is enormous. I mean, in particular in the past 30, 40 years or so. In synthesis, by reversal, we assume what was obtained last in the analysis to have been achieved already, and setting now in natural order as precedents what before were following and fitting them to each other, we attain the end of construction of what was sought. This is what we call synthesis. Now, Ali Behboud wrote in 1994 a paper for Centaurus on this matter, and Heinrich Guggenheimer reviewed it for Math Reviews in 1996, and he defines analysis and synthesis in this manner. Synthesis is clearly the construction of an algorithm. Analysis is a methodus inveniendi of such algorithms, and as such is an exercise in ingenuity and discovery. It is kind of in this sense that we will look at reverse analysis as a Pambuccian analysis. We will start with a result and we'll ask for minimal sets of assumptions from which it can follow. Now we look at what Descartes had to say about analysis and synthesis. In his second set of replies, he wrote, "It was synthesis alone that the ancient geometers usually employed in their writings. But in my view, this was not because they were utterly ignorant of analysis, but because they had such a high regard for it that they kept it to themselves like a sacred mystery. You will excuse that I gave you only the translation. You'll see many in the original language and what follows. So, well, why do you want to start with something and find few assumptions from which it's true? In general, you know that that thing is true in some kind of rich universe of assumptions. So let's see, who thought that this was of interest? Well, the earliest that I know of is Aristotle, who says, let it be granted that ceteris paribus, i.e. if the premises are equally well known, a proof from fewer premises is better than one from more premises because it produces knowledge more rapidly. Now, this seems to be obvious, but it is, as I said, in profound disrepute today. Today, from more premises is much better. In Western philosophy, it resurfaced as Occam's razor. And in a more mystical vein, we find it at about the same time in Meister Eckhart's sermon von der Unbedürftigkeit, on needlessness. That one is much more blessed who can dispense with all things and does not need them than he who has taken possession of all things because he needs them. And this is the original. That one is truly poor in spirit who can dispense with everything that is not needed. Der ist wirklich arm im Geist, der alles das wohl entbehren mag, das nicht nötig ist. So we skip now several centuries and we came to William Stanley Jevons. In logic, I hold that in all cases of inductive inference, we must invent hypotheses until we fall back upon some hypothesis which yields deductive results in accordance with experience. So here he expresses a reverse kind of sentiment. In deduction, we are engaged in developing the consequences of a law. We learn the meaning, contents, results, or inferences which attach to any given proposition. Induction is the exactly inverse process. So this same inverse thinking resurfaces in the work of the mathematician Hermann in 1890. So he says one can ask of the proof of a mathematical theorem that uses only those assumptions on which the theorem really depends. Here we see also a sort of purity of method. In other words, if the statement of the theorem says only about these things, then don't come with things that have nothing to do with the statement of the theorem. The least imaginable assumptions are the existence of certain objects and certain operations by which those objects are connected. If it is possible to string together such objects and operations without adding new assumptions in such a manner that theorems arise, then one obtains in these theorems a self-contained domain of science. So what he proposes is to take out of a certain discipline just a few principles, a few objects and constructions, and a certain assumption about them, and those would create a self-contained domain of science. For example, we've seen yesterday ordered geometry. Ordered geometry is, you can think, you look at Euclidean geometry, say, and you ignore everything that has to do with a metric. And then you can get ordered geometry. Or you could have gotten incidence geometry by ignoring order as well as congruent, as metric notions, and then you have something else. You have a self-contained domain of that science. In the same vein, Hilbert comments on the last page of his Grundlagen der Geometrie of 1899, the tenet according to which one should clarify the principles of the possibility of proofs is intimately connected with the requirement of the purity of the methods of proof, which have been emphasized of late by several mathematicians. This requirement is, after all, nothing else than the subjective form of the tenet followed here. In effect, the analysis performed here searches in general to shed light on the question regarding which axioms, hypotheses, or auxiliary means are necessary for the proof of an elementary geometric truth. So one would think that with such a solid endorsement, this kind of enterprise would have some future. And so I'm standing, well, it doesn't. Also in 1903, in a paper on figuring out how much do you need to be able to prove that in an isosceles triangle, the base angles are congruent, Gilbert writes, by the axiomatic analysis of a mathematical truth, I understand an investigation which does not aim to discover new or more general theorems relative to that truth, but rather aims to clarify the position of that theorem inside the system of known truths and their mutual logical connections in such a way that one can indicate exactly which conditions are necessary and sufficient for justifying that truth. It's again a very clear statement of a reverse undertaking. And also in his lecture notes before the publication of the Grundlagen der Geometrie, he would say, in modern mathematics, one exercises this sort of critique very often, whereby we notice the tendency to preserve the purity of the method, i.e. to use in the proof of a theorem, if possible, only the auxiliary means that the content of the theorem imposes upon us. The topic is also treated by Bertrand Russell in his talk, The Regressive Method of Discovering the Principles of Mathematics, which he read to the Cambridge Mathematical Club in 1907, and whose object is to explain in what sense a comparatively obscure and difficult proposition may be said to be a premise for a comparatively obvious proposition, to consider how premises in this sense may be discovered, and to emphasize the close analogy between the methods of pure mathematics and the methods of the sciences of observation. Now, what about the special case of geometry? Usually one looks whether something is true in one of the well-established geometries. If we look at Husser, though, he points out in his thesis of 1936 that in ihr leben wir selbst gemäß unserer leiblich-personalen Seinsweise. Aber hier finden wir nichts von geometrischen Idealitäten, nicht den geometrischen Raum, nicht die mathematische Zeit mit allen ihren Gestalten. So, in it, the world of the really experienced intuition, we live ourselves according to our bodily personal manner of existence. But here, we find no geometric ideality, not the geometric space, not the mathematical time with all its figures. So, The reason I think it is relevant to this is because the critique to this kind of undertaking that I just proposed is to say that, well, the really existing space has all of these properties. Why should I restrict myself to a few of them? And Husser tells us that that's not quite the case. And there's also a poem who tells us that that's not quite the case. The poem is La mer secrète. Quand nul ne la regarde, la mer n'est plus la mer. Elle est ce que nous sommes lorsque nul ne nous voit. Elle a d'autres poissons, d'autres vagues aussi. C'est la mer pour la mer, et pour ceux qui en rêvent, comme je fais ici. Jules Supervielle in 1938. So we see here that the sea, when nobody looks at it, is a different kind of an object. It has different fish. It has different waves. So it's a poetic version of the Husserian thought that in the world of experience, the space is not the geometric space. So when nobody looks at this, then it's a different story. So, as I said, these are an apology for doing this, is that usually the question is, well, why should we ask whether something we know already to be true, say in Euclidean or some classical geometries, are true under fewer assumptions? So, if you think of these geometries as the observed sea, to which we have superimposed the structures of our mind, then we would rather perhaps look at the sea when nobody observes it. So the proposal here is not to ask whether a certain established geometry can perform a certain task for us, but rather, what are the minimal assumptions for an undetermined geometry that would satisfy, that this geometry should satisfy, so the task can be performed? Let's go on to a real world example, because so far it seems perhaps too poetic. Imagine one wants to open a shoe factory in a certain location, and one does an analysis of the needs one has and the conditions and everything. Wouldn't one want to know what the minimum requirements are for running it? That would be a kind of reverse analysis. The version with this is the geometry you have to live in it would be to ask whether all the minerals on the Earth's surface can be found within 20 kilometers, whether there is a philharmonic orchestra, a theater, and an opera in the vicinity of the shoe factory. Well, what do you think the investors would do with this information? Well, we know what they did. They go to China, where there's abundant cheap labor available. Yeah. So it's a question of resources. It's what do you ask for this? So when you have an elementary geometric theorem to prove, it's just like this. You want to know what are the minimal assumptions, the rudimentary properties of a world in which this would be true. So it isn't that poetic. I mean, after all, people do this all the time at some level. Not that there is anything bad with it being poetic, but I try to find justifications from every kind of field of life. Now, you would say, okay, we've heard about such an undertaking. It's called reverse mathematics. What's the difference? Well, there's a great difference. Reverse mathematics believes that there is a certain theory, a certain weak second order arithmetic, which is given from Mount Sinai. And then you ask, is this theorem, what does it require more than that? But we don't have something like this. We don't have the Ten Commandments or something that came from Mount Sinai. There's no holy thing. We don't know. We don't have a set of axioms that are a list of axioms that are acceptable, and we have to get to those. So how do we approach this then? So when you have a theorem and somebody asks you, well, what's a minimal set of axioms for it? You have to invent the axioms because they're nowhere to be found. So this is similar. So this is an art. At the end, you can't say this is where I had to go because of. So it's not far removed to that of a playwright, the way Lessing described it in his Hamburgische Dramaturgie in 1767. He says the poet finds in history a woman, which is Medea, who killed her husband and her sons. Such a deed can evoke fear and pity. So he decides to treat the case in a tragedy. Insofar as he more or less deserves to be called a poet, he will become aware of either the implausibility or of the thin shortness as the greater deficiency. So either he sees that this is completely plausible, or he thinks this is too short an action. So one of these two will be displeasing. Should he find himself in the former case, then he will be foremost concerned with the task of inventing a series of causes and effects, according to which those implausible crimes could not but have happened the way they did. So here we see a reverse undertaking that a playwright would undertake. You start with an end, and you have to build up a completely convincing flow of events that get from those conditions to the given end. Also, the difference here is the classical way to approach geometry is I want to construct a geometry where everyone is happy, that is super rich, where you can prove anything and so on. What we're trying to do is to make individual geometric theorems happy, not everyone. So the way Boris Vian put it in L'écume des jours, ce qui m'intéresse, ce n'est pas le bonheur de tous les hommes, mais celui de chacun. Now we come to one of the first examples of this, if not really the first. It comes from a poet. This is not somebody who happened to be also a poet. This person, under the name Ion Barbu, a pen name as a poet, was, with about 3 others, the major poet of the interwar period in Romania. In other words, you can't graduate from high school without having gone through his poetry. He happened to be a mathematician as well. And he studied in Göttingen, but at the time, Gilbert wasn't in that great a shape. And he wasn't interested in, he wanted to study number theory there, but he wasn't interested in analytic number theory in the style of Landau. So he wrote poetry and came home to Romania without a degree, which he defended then in some geometry in Bucharest, and then started, doing his foundational geometric work. And in 1936, in the space of 60 pages, he set out to reversibly analyze a theorem recently proved by Dimitrie Pompeiu. It turns out it's much older. So something like Möbius should have known it. But at the time, this is not known. It says, if ABC is an equilateral triangle, and P is any point on its plane, then the segments PAPB, satisfy the generalized triangle inequality. What does that mean? That each of them is less than or equal to the sum of the other two. Okay, well, Barbignan took individually all the axioms from Hilbert's Grundlagen geometry and asked if this is dependent on it or not. Basically, can you even phrase it without those? And he figured out no for most of them. And then he comes to the parallel postulate. Now he comes to the continuity axis and says, no, those don't matter. And he shows that. And then he comes to the parallel postulate and says, no, it doesn't matter on that as well, because he shows it's true in hyperbolic geometry, which takes an enormous amount of space. And he's somehow unaware at the time, or at the moment of writing the paper, because he surely knew about the paper, of Max Dehn's paper of 1900, where Max Dehn shows that, well, there are these semi-elliptic geometries. In other words, there are models of absolute geometry where the sum of the angles of the triangle is greater than 1/8 by a tiny bit, by infinitesimals. So he thinks that this implies that, he dismisses that, he doesn't treat that case. But you can see that even in that case, it's not true. So it turns out that if you have absolute geometry as a base theory, then Pompeiu's theorem is equivalent to the sum of the angles in a triangle is less than or equal to 1/8, the two right angles. So he showed that it's independent of the parallel postulate, but you need to replace it with a statement that says, I can't be in the semi-elliptic case. So it is set up as a reverse analysis, which perhaps justifies that all of these poetic references were not in vain, but actually this is something that poets like. Now, one might ask, isn't this kind of vacuously true in certain places? In other words, yeah, there is this problem here, but I don't know how to remove it. So I think it's irremovable, or it is here.
On the red section, the ring, sorry, you should drag it.
Drag it down like this? No. From this.
From the center of the green bar. Try to hold it, to click and drag it.
You can do it upward.
Like this. Move it here. Yeah, perfect. Let's move it back then. Okay, great. Now we're having everything written here. So one would ask oneself, okay, well, the story is about an equilateral triangle, right? Well, what if there are no equilateral triangles in some absolute geometries? After all, remember, absolute geometry doesn't have the circle axiom. If you think of proposition 1 in Euclid's Elements, he gets an equilateral triangle by getting the intersection of two circles. Okay, well, is there an equilateral triangle at all in absolute geometry? Put differently, does the angle of 120 degrees exist in absolute geometry? Well, because if it exists, then you can form a kind of Mercedes thing and just get your triangle. Huh? I was surprised that this was unknown. I proved it in 1998 with a great amount of difficulty. It's not easy at all to show that there exists an equilateral triangle in absolute geometry. So in Hilbert planes. So yeah, it's not vacuously true. These actually exist everywhere. In the early 60s, Paul Erdős proposed a problem for the American Mathematical Monthly that was proved by Mordell, who was a number theorist. The problem said in any triangle, the sum of the distances from an internal point to the vertices is greater or equal to twice the sum of the distances from the point to the sides of the triangle. Let's do some drawing here. So I have a triangle and a point inside it. I join the point with the vertices, and then I drop the perpendiculars. The sum of these, so let's say PA plus PB plus PC is greater or equal than twice the sum of these. So this is P, A, B, C. Let's call this M, N, L, and N, let's say. Yeah? Then this is greater than 2PL plus PN plus PM. Yeah? So this was proved in Euclidean geometry. There are multiple proofs of it. But the question of the reverse mathematician would be, what do you need for this? Well, you need a lot, actually. You need to be able to draw perpendiculars, obviously, because that's what it says. Then you need to be able to add segments. So you need something like a segment transport. So you put them together so you know what the sum is. You need to have some notion of order to know what is bigger than what. So it turns out that you need absolute geometry to have any chance of saying something like this. And in 2008, I shown that this is equivalent, again, just like Pompeius's theorem, to the sum of the angles of a triangle is less than or equal to 2 right angles. So what about if we move now to Johannes Hjelmslev? Johannes Hjelmslev wondered what it takes for the medians of a triangle to be concurrent. He asked the same thing for the altitudes. And eventually in 1967, Bachmann showed that you need extraordinary little. You need a few things about some reflections, much less than the metric planes that we have discussed in the past. So for the altitudes to intersect, you need really, really little. For the medians of a triangle to be concurrent, what do you need? And he dealt with it in 1929. And what you need is the theory of metric planes, which contains these trivial things that there are at least 2 points. For every 2 different points, there is a line incidence for those points. If A is orthogonal to B, then B is orthogonal to A. Orthogonal lines intersect. Through every point, there is to every line a perpendicular, which is unique if P is incident with L. To every line, there is at least one reflection in that line. And the composition of reflections in 3 lines, which have a point or a perpendicular in common, is another reflection in a line. If you have these, then you can prove that the medians, so suppose you have a triangle and you're told that each side has this midpoint. And then you look at the joining lines of vertices and opposite midpoints. Usually you expect them to have a point in common. What Hjelmslev shows is that the composition of the reflection in these 3 medians is a reflection in a line. And that tells them that your 3 lines have a point or a perpendicular in common. They can't have a perpendicular, so it's going to be a point. It's not a point, the point must not necessarily exist in that plane, but the confluence of the 3 lines can be witnessed by this fact. Because if you think about it, you can extend these metric planes to projective planes. So those 3 lines may not have had an intersection in your world, but they had one in the projective extension. The proof is extraordinarily long and complicated. And so you can think, if you want to start with this statement that the medians are concurrent, and you're asking, well, how much do I need for this? Then you actually need all this stuff. I mean, if you don't have that the composition of reflections is here, then this is certainly not true, because then the whole structure falls apart. And you can't do it with just the composition of reflections in 3 lines which have a point in common only and drop the others. So none of these work. So you actually need this whole thing if you want to prove that. But here I want to show that this arsimbenienti, these regressive analysis leads to different places that are incompatible with each other. And here is another proof for the same thing in a completely different setting. So the previous setting was a setting of reflections in lines, perpendiculars on lines. Lines are perpendicular. This is a world where only points exist. And there are 2 operations on these points. One is the reflection of one point in the other, which is written A times B. So that means the reflection of B in A. And the other operation is the midpoint operation. Given 2 points, it gives you the midpoint. Notice the other one didn't have a midpoint at all. And in fact, there are models without midpoints. Why? Well, because we have stated it in the case in which the midpoints exist. It's stated as a universal statement, and in that sense. So, and well, not necessarily universal, because in the end you say there is a line, the being in a bundle involved having this additional line. But the hypothesis was, okay, everything exists, then this is true. In this one, we just have no lines at all. There are only points in this thing. And what do we need is axioms. This axiom says that the midpoint of, let's go back to the drawing of things. This. So A, B. Okay. The reflection of B in A. I'm drawing a line, although there is no line. There's only points, right? So B times A. Yeah. This says that the midpoint of these two is this. Oh, the B in A. Sorry. So the B in A is what? You go from the last to this. So it's, let's cancel this. Okay. And now let's do it again. A and B. Okay, so the reflection of the last thing in the first thing, yeah? So reflection of A in B, yeah? This is B dot A. And now this says that the midpoint of these two is this person. So basically it defines the relationship between midpoint and point reflection. It says that they're kind of inverse to each other. Now let's get rid of this and hope things go well. Yeah. Oh, no. What is this? Perhaps now it goes this way. Yeah. Okay. The next one says this. Let's go again to the drawing board. So I have A and B. This is the reflection of B in A. Then I take this and reflect it in A. I take this and reflect it in A. And what do I get? Back to B. So this tells me that reflection is involutory. So that its square is the identity, if you want to put it that way. Yeah. Okay. Now for the next ones, I do have drawings, so it shouldn't be a problem. So then I have another axiom that we'll see in the next picture. And finally, this is not an axiom, this is what we want to prove. This is the statement that the medians of a triangle are concurrent. That thing. And what can be shown is that 1, 2, and S12, so the first trivial things, and the only thing with some substance that looks like that, yeah, imply the median intersection theorem. This is in a paper, in a recent paper by me and Yuri Movsisyan. We didn't actually prove this. An automatic theorem prover did it for us. It takes 24 lines, actually, of using those things and so. So by hand, I don't see myself being able to do that. It's done by prover 9. I had an even longer proof with the prover E. And then the referee pointed out that it gets shorter. So in fact, all my work with provers was in vain. I had to read the output of the referee and to make it into something understandable by myself. So now what are these? What's the S12 and what's the S13? Well, here you see the S12. I mean, what's the geometry behind it, you know? Because these look like algebraic things. It looks like you're gonna distribute the B first to the A and then to the C, right? And this looks like, well, you're flipping these two. You're flipping the B and the C in here. Yeah? So what is this? Well, let's see. So this one said what? Said that if you reflect B in A dot C, then you get the same thing as if you reflect C times B into A times B. Okay, so reflect B in A times C. Here it is, yeah? Okay, so look at what happens. This is B being reflected in A times C, right? Okay, and this is C times B being reflected in A times B. That's exactly what that said, that these are the same. So what does it say? Let's see. If you look at this triangle here, these are midpoints. So A dot C is the midpoint of this. C is the midpoint of B and C dot B. Yeah? This is the midpoint of that. This is also the midpoint of this, right? So it says that if you're in this situation, so this you could do all the time, right? You start with an A, B, C, and what do? You reflect B in A first, then you reflect B in C, then you reflect C in A, then you reflect B in this. Now you have 3 points. What the theorem says is that this will be the midpoint of these two. Okay, so that's a statement of a Euclidean kind of metric. Because in another way, you can think that it says that the midline here is half of this. That's a thing that works when you have a rectangle in your plane, right? So it's a form of the Euclidean metric. Yeah? It's a very weak form in this statement, in this points and reflections only language. So we clarified a bit what S12 was about. Now, what about this? What's that saying? So that says, if you reflect C times A in A times B, then you get this. So in A times B, you reflect C times A, so this. Huh? So A times B times, no, that comes from here, right? C times A times B, that's the reflection. Yeah? It says that you should get the same if you reflect this in this, because remember what it says is that you can flip B and C, right? Okay, so let's start with A, B, C. Okay? I can start with any A, B, C, then reflect A in C and get this. Reflect A in B and get this. Now reflect further C in A and get this. Reflect B in A and get that. Then I'm told that the reflection of this point in this and this point in this coincide. What does this have to do with the medians of a triangle meeting in a point? Well, in this triangle, in this big one, yeah, these are medians. Yeah. So we're told that if you have two segments that intersect each other in the rate 1 to 2, then these two are the medians of a triangle. if you go now for the other two, if you go now for the median here, you will repeat the same thing and you will know that it goes to the same point. You know? And by the way, although this is very Euclidean as well, why? Because we know that in non-Euclidean geometry, there is no triangle for which the two medians meet in a point that divides each into 1 to 2. Okay? So this is a particularly Euclidean metric thing. However, if you take this as an axiom, you can't prove this. In fact, there are models of independence. Even if you take many more things like S11 and many more other things, you still can get to that. So in the world of point reflections, these things that apparently are the same have a hierarchy of strength. So this is another minimal set from which you can get this. The two, though, what we talked about earlier, the metric planes and these, are incomparable. You can't say this is simpler or that's simpler. And you can't say, well, which one has the purity of method advantage? Because you could say, well, reflection in points is a notion that is in there, right? I mean, you know what midpoints are, so you know what reflection in a point is. And so the second axiom system seems to be using the terms of the theorem, but it uses the Euclidean nature of that metric, which the other one does not. The Hjelmslev proof on metric planes does not use that specific thing. So these two languages do not communicate. I mean, you can define what a point reflection is in any metric plane, that you can do. However, the S12 will not be satisfied. It's not true. So the existence of midpoints is not true in that world. But you can say, okay, let's add that. Well, then S12 is not true. What about the other world? Well, the other world is completely doesn't understand what those people talk about because it doesn't know what lines are, to say nothing of reflection in a line. So it's completely at a loss about what the discussion is about. So it's only us humans. So if you want at a very formal level, it's impossible to decide which one is, you know, preferable or simpler or any of these things. You can say that there is more depth perhaps in the Hjelmslev one because it shows the absolute nature of the confluence of the medians. But here you must have a historical background and understand, you know, I mean, absolute geometry has to have appeared because of some reason. You want it to be separate of Euclideanity, of the Euclidean nature of the metric, all of these things. The formal level cannot decide these things. So another such example of a reverse statement is obtained when you look at the Erdős-Troost problem. In 1956, they came up with this nice little gem of elementary geometry. If you have something like this, this is supposed to be, I don't know, something like 4,000 years old or so. So it seems that people knew it even then, the Erdős-Troost problem. What do we see on this base here? Well, we see a triangle, don't we? Yeah. And the vertices, right? And we see here 3 points on the sides. And we see how there are 4 triangles formed. And which triangles are having this pattern here? The corner ones. What does Erdős say? It says that always, regardless of how you do this division, it's one of the corner triangles who has the least area of all the 4. Okay. So you wonder, what do you need for that? Well, you would say the concept of area is a very complicated one, isn't it? Well, it may be. But what do we need actually to show? We need to show only that, comparatively speaking, each of these people here is that, well, not each, that the smallest of these people, is smaller than this. So what you need to be able to do is to compare the areas of 2 triangles that have a side in common. This can be done in both the Euclidean, in the case of an Euclidean metric, and in case of a non-Euclidean metric. But we don't even try in the case of a non-Euclidean metric because we know it's not true. In fact, if the points are the midpoints of those, yeah, then no, they're equal in the Euclidean case. But in the hyperbolic case, the middle one is the smallest. So we know from the beginning that in our reverse analysis, we shouldn't think of absolute geometry or so, because it's not true in hyperbolic, so forget about it. So we know that some amount of Euclidean nature needs to be there. So what should we abandon then? We should abandon all notion of metric. What is left then? Well, there needs to be some order because you're talking about smaller and bigger, right? So order is unavoidable. And we'll have the uniqueness of parallels. So we have what is called affine geometry, ordered affine geometry. Now, with nothing, you can't get very far. With ordered affine geometry, you can't get this. What you need is a configuration theorem. And the configuration theorem will be the minor Desargues axiom. And you want to see how that works. I mean, what that is, and it's the following thing. You got 3 parallel lines. You got a triangle here. And another one here. And you know that this is parallel to that. And you know that this is parallel to that. Then the minor Desargues axiom says that these are parallel as well. Yeah, so you're on 3 parallel lines. You got 2 triangles with the vertices on those lines. These 2, this and this are parallel. This and this are parallel. Then the other 2 are parallel as well. These are called translation planes because, as you notice, it means that if I translate this structure here, then the third line, so if I translate this to this, I know this becomes that and this that. But does the other one become that? And the idea is yes, it does. So you can have a reasonable calculus of translations in it. And that's what it requires. So this theorem is true in this very restrictive world. Okay, let's get out of here, do a little things that, okay, now, Similarly, we have Lexell's theorem, who Lexell was a 19th century astronomer, which says that if you're given two fixed points A and C, then let's look at the locus of the points B for which ABC has a fixed area. In the Euclidean case, we know there are two parallel lines, one up, one down. This is no longer true in hyperbolic geometry. It's a hypercycle or whatever, it's a bad thing, a second degree curve. However, the locus of the midpoints of these, of BA and BC, always lies on two lines, regardless of the metric. So it's true in hyperbolic geometry as well. So the question is, what do you need for this to be true? First of all, you would say, well, there's a notion of an area. Isn't that very complicated? Well, it is, but we can do it. All you need is non-elliptic metric planes in which every point pair has a midpoint. The proof is very complicated, and you have to rephrase it to have a meaning of area in a place where there is nothing but perpendicularity and reflections. So another reverse analysis. Here's another reverse analysis where you see how weak the geometry is that you obtain. In 1960, it was shown that if you give me an obtuse triangle, then I can triangulate it with acute triangles, with 7 acute triangles and not with fewer. So every obtuse triangle can be 7 triangulated with acute triangles, and you cannot do it in general with fewer than 7. The question is, how much geometry do you need for this? This was done in the Euclidean set. So obviously you need orthogonality and order, because the question is, what's acute, right? And you need order because, well, acute means it's less than something, so that's there as well. So what are the minimal requirements that orthogonality and betweenness need to satisfy? So we prove this. Betweenness, the usual axioms for, giving rise to dense unending orders, as well as the Pasch axiom. And with it, you can define acuteness. And you need to be able to raise a perpendicular on any line on a given point. You need to say that there are no self-perpendicular lines. You can drop a perpendicular from a point C not on a line AB to that line, which is this. Orthogonality is a symmetric relation, you need to say. And the perpendicular from a line not on a line, on that line, is unique. Perpendicularity is a relation between lines. If BAC is acute, then CAB is acute, which is another way of saying that you can't have two right triangles with the same vertex, one within the other. This axiom was actually used by Gilbert for arbitrary angles. And then you can prove it. So notice the axioms say nothing about things like the altitudes of a triangle meeting a point or any of these things. It's just that you can drop perpendiculars. It's not even said that you can draw reflections in lines. You don't even know what a reflection would be. There's no notion of congruence, if you've noticed. Everything is just orthogonality and betweenness and trivialities about them. And with that, you can show this. This I've shown with my student Johannes Hjelmslev in 2011. Similarly, you can look at a theorem by Alexander Harajishvili, who showed that if you were to cover all the points on the real Euclidean plane with 3 colors, then there's always a rainbow triangle that is obtuse, acute, and right. Rainbow means its vertices are of all the 3 colors. The question is, what do you need for this? Well, for the obtuse case, you just need exactly the axiom system that we have for the 7 acute triangulation, to which obviously you have to add an axiom saying that every point is of 3 colors and that all of them are used. For the acute one, you need something else. You need to know that if you have 3 points, A, B, C, which B between A and C, then on the perpendicular from B to AC, there is a point such that this is acute. So you can raise this enough so that that's acute. And for the right rainbow triangle case, it is enough to have the existence of reflections, no 3 reflection theorem at all, just the existence of reflection. And for the Loschnitt axiom, you need to know that if this is orthogonal to this, and you raise here 2 perpendiculars, then these meet. Now, the Sylvester-Goloy theorem says, it was proposed in 1893, that if you have a finite set of points that are not all on a line, then there is a line through exactly 2 of the points. Okay, so you have a finite set of points, not all on a line, then there is a line that goes through exactly 2 of them. I did a reverse analysis of this, and it turns out that there are 3 compatible minimal sets of assumptions. One is that of ordered geometry. But ordered geometry this time where you don't need to say that the order is dense or unending. So you need both IP and OP, because the proof that OP implies IP used the unendingness thing. Without it, you need both. It's not known whether OP is needed. So nobody knows whether this would be true in a geometry with just IP. You can prove it also based on just existence of perpendiculars and some things such as that in a triangle, the side is less than the hypotenuse, and this thing that we encountered last time. So you don't need just a little bit of order and this. A little bit of order means no posh, just a little bit of order on segments. And based on a proof by Chen in 2006, it basically works in metric planes. So all you need to know is that you can add segments. So you have a congruence notion, and you know you can add segments together and say, what's the sum of them? Another such problem was that for every point P in the plane of a triangle ABC, there exists a point Q inside or on the sides of ABC, for which all these distances are less than the corresponding distances from P. And if P lies outside of the triangle ABC, then Q can be chosen to both lie inside the triangle and be such that all inequalities that you see above are strict. This was the second part was left open completely in a paper by Aja and Martini. The second part was proved in a very complicated way by using both Zorn's lemma and Bolzano-Weierstrass. So I showed with 2 students in Armenia that what we need is the order axioms, including Pasch, existence of perpendiculars from points to lines, the existence of the perpendicular bisector of a line, segment inequality defined in terms of the perpendicular bisector. So you would say that PA is greater than PB if P lies on this side of the perpendicular bisector. We know what sides are because we have order. Existence of point reflection, so you can reflect a point in another point. And the axiom that says if a segment is smaller than the other, then so are the halves. Which you say by saying that, well, if you have A, B, C, so B is between A and C, then the halves here are in the same relation. You half everything, then your A is still in between. That's all. Obviously, this is an absolute geometry that is much weaker than all geometries that we've ever encountered. Another problem is a problem that was posed at the International Mathematical Olympiad in 2011 about this. In 2011, the Olympiad was in Amsterdam, so it was selected perhaps because it speaks about the windmill. And it says you have a finite set of points and you start with a line that goes through some point, and then the line rotates until it hits another point. This original point is called a pivot. When you hit the other point, that's called a pivot. Now you continue with a clockwise rotation always around that pivot until you hit another one. Now this other one becomes a pivot and you continue this way. Well, the problem has to show that there is we can choose one of these points and a certain line that you, a certain starting position for this windmill process, so that the windmill will go through all the points of the finite set indefinitely many times. Obviously, if it goes once, it will go indefinitely many times. Now, you'd think that this has something to do with rotation and who knows what. Well, you can rephrase all this thing in ordered geometry and prove it, which is what I did in the paper. So the official proof talked about parallels and things, and no, you don't need any of that. I'll skip to this one. I'll just say the theorem, but I won't go into the details of the proof. This was a problem that was published by van der Baden in something like the 60s in Elemente der Mathematik. Turned out that it was probably known by Euler already, that if you have a space pentagon where all the sides and all the angles are congruent, then this pentagon must be the regular flat pentagon. So the angles, instead of saying angles, you can say diagonals. So all the sides and all the diagonals are congruent, then you have to be a space. This is no longer true if you go to higher dimensions. So you have to be a 3-dimensional world for this to be true, which is what Botema showed in 73. There are 2 proofs, and I followed a reverse analysis of both. You end up with things that are way too weak to construct any geometry. And well, there are lots and lots of axioms, and more, and here you have the axiom systems for both groups. Now I'll go over to arithmetic, which you would say, what does that have to do? Well, it shows you that the reverse process can be, to a certain extent, pursued in different settings. As I said, there is reverse mathematics that does it, but reverse mathematics believes in a certain standard theory. The question is, can you do it outside of geometry without believing in this standard theory? And here I will look again at an elementary statement and ask, well, what is needed for this? Only this time the statement is about positive integers. Shatunovsky in 1893 proved that 30 is the largest number, all of whose tautatives, a tautative is a number less than that number, but prime to this number. Huh? So if you have 6, for example, its tautatives will be 1 and 5. For 10, the tautatives will be 1, 3, 7, and 9. Yeah? So numbers less than it, but that have no common divisor for them. So Shatunovsky showed that 30 is the largest number, all of whose tautatives are actual primes. Here you count 1 as a prime. I just for make a little exception. His original proof relied on Chebyshev's theorem, which says that for every n there is a prime between n and 2n if n is at least 2. Yeah? Max Dehn spent some time at the University of Münster, his first job. And there he had a probably undergraduate student, H. Bonze. I never could find out what the H stands for because he doesn't show up in later publications. Who suggested, couldn't you find an easier proof of this theorem that doesn't rely on this, very heavy machinery of Chebyshev's theorem? And Bonze had found one. He used, in fact, what is called today Bonze's inequality, which says that if you multiply all consecutive primes up to some k, and the k is at least 4, so you multiply at least 2, 3, 5, 7, yeah? Then you get more than, this is more than the next prime squared. And this he showed not that complicated. So Bonze's proof was popularized by Rademacher and Toeplitz, who wrote this book that is translated as The Enjoyment of Mathematics, and it's available now in the Princeton classic paperbacks, where it is praised for its simplicity, as it depends entirely on pure reasoning. Lediglich an den nackten Verstand appelliert, is what they wrote in the original 1933. So the question clearly appears, can we find a formal reason why it is? Because this is kind of a feeling, an intuitive thing. Can we say, well, the proof from Bonze's inequality is simpler than the other one? And this is what I have embarked on. So you can't say it's simpler because, if you're stuck with the natural numbers, with the standard natural numbers, it makes no sense to speak of simpler or more complicated because both of them are true in the natural numbers. Same is true of the standard axiomatization, say I delta 0 plus x, where people try to show everything in elementary, because both are true in it. So what do you do? Well, I was thinking, okay, let's look at these, at Chebyshev's theorem and Bonze's inequality as axioms themselves, based on a very weak arithmetic, which is this PA minus. So arithmetic where you don't say anything about induction, which is the same thing as the positive cones of discretely ordered rings. So you just say that addition is associative, commutative, same thing about multiplication. You say that it's distributive, you explain who is 0, who's 1, you explain what that less than is transitive, that it's irreflexive, that it's total, so anything can be compared, that it's compatible with addition, and it's compatible with multiplication by positives. okay? And that there exists the subtraction. So if y is greater than x, then there is something from x to y. So that's the y minus x. Yeah? So you have a y minus x function, if you schoolemize that. Then you say that 0 is less than 1, and you're saying that, you know, anything positive is either 1 or more than 1. That's the discretely ordered. So you can't jump by less than 1. Yeah. And everything is 0 or positive. So we're interested in the positive cone only. Okay, that's all there is, PA minus, yeah? So it doesn't look like really arithmetic because except for the discreteness part, there's no arithmetic in it. But you can define in it two notions of a prime number because after all, our story was about primes, right? So we should be able to express that. One is by saying that it is irreducible, right? You can't, it's not the product of any things that are not one. So that none of them is one. And the other is that if it divides a product, yeah, then it must divide one of the factors. So the first is called irreducibility, the second is called primeness. Primeness implies irreducibility. The converse is not true in PA minus. Okay? We'll take this as an axiom. So above PA minus, we'll say all irreducible are prime, to simplify things. The notion of co-primeness can be defined, and now you have several statements. One is S30 that says, well, 30 is the biggest such thing. Okay. The other says, you can say there is such a biggest thing without specifying who it is. That's S max. There's another one that says there is an upper bound on such things. It doesn't say that there is a biggest, but there is something from where on there are no such things. Okay, you can prove in PA minus that S max is stronger than S upper. So just saying that there is an upper bound doesn't imply there's a maximal thing. It's complicated, but you can construct models for this. It's not known whether, if you say there is a maximal one, then that has to be 30 in PA minus. Now, Chebyshev's theorem is something you can express. And the PIs, you can choose whichever, because we know that primes are irreducibles or prime. And here is Bonze's inequality, which just says that if you have a product of all the primes less than something, then this is the next prime, then you have this. There is, it doesn't say the next because you can't say that. And you can't say that they were all the previous ones and only that, but you say something similar, that there is a prime greater than this so that the square is less than that. So you find a way to express this in this very poor language. Then you can show that if you have Chebyshev's theorem, then you can prove Bonze's inequality. Right? We're always in the presence of I is P, right? But vice versa, even if you add induction for all open formulas, you can't prove it. Which says, well, Bonze's inequality is simpler. Good. Now, if you look at just PA minus and you take all of CT, so Chebyshev, you can't prove even the weakest of all the Shatunovskys, that there is an upper bound on this. Obviously, you can't do this with a weaker. But if you add this, that there is a greatest prime dividing a certain number, this number U, which has the property that it is divisible by all primes smaller than any of its prime divisors. So you have a number U that has this property. The axiom GP says that this number must be divisible by a largest prime. Yeah? Put otherwise, that there is this, that this number in the set of its prime factors, there is the greatest one. So if I have this, then I can do a whole lot. Then just with Bonze's inequality, I can prove S30. Now, to really have shown that Bonze's proof was easier than the one with Chebyshev's theorem, one would need to show that Chebyshev's theorem is not true in this. Yeah? But this we don't know. But at least we have the setup of what it takes to show these things. So the moral is that even in arithmetic you can follow, but the difference with the geometry is still huge. In arithmetic you can't say, I'm not going to even consider that plus exists or time exists. Or plus doesn't need to be associative and commutative, because everything collapses. In geometry, you can do that. You can get rid of everything. We'll come back to this at some other time. So we see that in geometry, we have deductions that are the essence. So we see there is a certain geometrical thinking that cannot be modeled in algebraic terms. And that in our reverse analysis, we have reached at this secret seas, these geometries that are way too weak to allow any kind of algebraization. Because algebraization, you know, requires some this arc, some pappus, some something. This have nothing. Now, I'm trying to ask some of the possible critiques of this, which I pointed out in the beginning. People would say, well, the real world is so much more generous and you're trying to take away so much from it. Well, why would you do that? One possible reply comes from Simone Weil, who says that life forces us to believe what we need to survive. And this servitude has been raised to the level of doctrine under the name of pragmatism. And you know, that shows that in a serious investigation, one shouldn't be a slave to this servitude. Now, you might say, why is it that people are against this? Against everything that you've heard today. And here I am quoting a very powerful mathematician, very influential in the 20th century, well known for the Atiyah-Zinger index theorem. He received the Abel Prize and so on. So what does he say? Why is this no good? So much mathematics is produced that it is not possible for all of it to be remembered. The process of abstraction and generalization are therefore very important as a means of making sense of the huge mass of raw data, that is, proofs of individual theorems, and enabling at least some of it to be passed on. The results that will last are the ones that can be organized coherently and explained economically to future generations of mathematicians. So here we see an administrative kind of reason why this is all junk. Because obviously these are very many proofs, many lines for each individual theorem. This is exactly what's bad. We shouldn't do that. We should get strong means by which everything is destroyed, not these weak means by which you have to just get one theorem and then the next doesn't work with that. I'm not sure though that this method works with memory as well, because the question is, what can you pass on? Because this highly generalized and abstractized thing, if you look at his own theory, the Atiyah-Zinger, I mean, to just understand what it's about, it's below 1 in 1,000 mathematicians that understand it. So the idea that it will be passed on greatly is doubtful. Or, you know, if you look at algebraic geometry, which is the fashionable thing, I mean, probably it's 1 in 10,000 to understand what's going on there. So it's not that easy. But I'm showing you that this is completely out of the mainstream mathematical idea. Now, the stuff with geometry is true out there, and the out there is generous, shouldn't be taken seriously. In fact, Giordano Bruno told us we shouldn't, because he said, altro è giocare con la geometria, altro è verificare con la natura. So what we have done is giocare con la geometria. But the people who say, well, reality is something else, well, that's something else altogether. He knew this already in 1584. Gilbert told us the same thing in 1898, which I've mentioned already in my first talk, but it's relevant here as well. He says that a homogeneous continuum that would allow indefinite divisibility and would thus achieve the infinitely small cannot be encountered anywhere in nature. So the standard thing that mainstream mathematics considers stuff over the real numbers or over the complex numbers cannot exist anywhere in nature. So even the servitude of pragmatism justification doesn't hold water. So the infinite divisibility of the continuum is an operation existing only in thought, only an idea, which is refuted by our observations of nature and by the experience drawn from physics and chemistry. Put differently, we find inspiration for why this should be justified in no other than Tom Sawyer, because he tells us that, why drat it huck? It's the stupidest arrangement I ever see. You've got to invent all the difficulties. Well, we can't help it. We got to do the best we can with the materials we've got. Anyhow, there's one thing. There's more honor in getting him out through a lot of difficulties and dangers, where there weren't one of them furnished to you by the people who it was their duty to furnish them, and you had to contrive them all out of your own head. Here he talks about liberating Jim by the very sophisticated method, which was supposed to be much more adventurous. So we also had to invent all these difficulties because they were never given to us by the people who it was their duty to give us. And a similar answer came from Jacobi to Legendre, who, after the death of Fourier, he says, il est vrai que Monsieur Fourier avait l'opinion que le but principal des mathématiques était l'utilité publique et l'explication des phénomènes naturels. Mais un philosophe comme lui aurait dû savoir que le but unique de la science, c'est l'honneur de l'esprit humain, et que sous ce titre, une question de nombre vaut autant qu'une question du système du monde. So, with these, I end the talk today, and wait for your questions.
Any questions from the audience or at home?
I have a couple of questions.
Okay, on you go, Pierluigi.
Thank you, Victor, for your extremely interesting and stimulating lecture. So I have just a couple of questions. The first one is whether, in your opinion, it is correct to say that the pre-Euclidean geometry Hippocrates of suppose for
the connection is really poor.
Can't hear you.
We can't hear you right. The connection is poor. It started getting bad and then it got worse.
I think this is
their approach to the Rota elements book. This is the first one.
You did? Because it says what? It says, he already lost completely connection.
Yeah,
But he had a very interesting thing about San Pablo, or what was it? I don't know.
I didn't hear well.
Because in the end, he said something about the Rota, but I don't know what it could have been.
We can try this.
Could he call in somebody on the phone?
Well, I have a question.
Sure.
It will be really useful to try to find a sort of fundamental system for geometry. So, as you said, in arithmetic, we have some 5 blocks, very important blocks of. The idea is to find every theorem which is the right block to connect this theorem. Which is the minimum block on which we can prove the theorem.
Yeah, I mean, look.
Hierarchy in geometry. So we have, I don't know, absolute geometry, the Euclidean, the hyperbolic, the complex, the metric, and so on.
Yes, you can go in that manner. So you can say, okay, here is incidence geometry, then ordered, then parallel, there is just pure orthogonality or congruence. Then you have absolute, then you go higher. But these are already geometries that are rich. In other words, you put kind of everything you needed in terms of those notions that you had there. So that is a way of going about it, but it may again be not a very parsimonious way, because perhaps not everything from there was needed. For example, if you look at the Sylvester-Goloy theorem, we don't know if outer pasch is needed. You'd say, okay, this is true in ordered geometry. Yeah, but ordered geometry itself has, some things which are open, and, we know there is a weaker ordered geometry that has just inner pasch. So everything that is true in ordered geometry, you can ask yourself, what about in inner pasch geometry? So the analysis goes deeper than just to which it belongs, to which of these blocks it belongs, yeah? That's obviously the first thing you're asking is if the notions contain stuff like area, for example. It seems like area requires a lot, But then you notice that, well, not necessarily. As you've seen in this example, we could do it with just reflections in lines, without order, without anything. That's unusual. How can you do that? Well, you can. We could also do it in an affine setting, so without metric at all. So some of these notions leave certain traces in weak geometries. And those traces allow us to reformulate the problem so that it's meaningful in that world. So I think, yes, you're right that on a first look, you associate kind of where the problem belongs. But if we look at this Haja-Martini theorem about, the point and the triangle and the distances, then you're thinking, well, where does this belong to? It appeared to belong to absolute geometry, right? Because it speaks about measuring distances and realizing they're less than other distances. But when you look what's needed, it's way less than all of absolute geometry. So all of these blocks that you were talking about contain a very rich theory. So inside it, you could ask, do I need this? Do I need that? And so, did I answer it somehow?
Yeah, so this really is far more messy.
Yes. Pierluigi, you're back.
Yeah.
And with
Sorry.
a much better audio.
Yeah, I'm sorry, Matt. My internet connection is not stable today. Okay, thanks for your extremely interesting and stimulating lecture. I have a couple of questions for you. The first one is whether, in your opinion, it is correct to say that the pre-Euclidean geometry, for example, Hippocrates of Chios, propose a sort of inverse geometry in his elements, because if I remember correctly, the approach of the Hippocrates is to study the axioms for solve problems, the principle to solve problems, and not to create a sort of closed system in which every problems of every geometrical problems, plane or can be solved. It's correct for you, this interpretation, or?
It's very hard to say because we don't have his elements have not survived to us. So I think you're referring to the few references that we have to him, right?
Yeah.
Yeah, if that's what he did, then you're absolutely right. We have the first, and there is an interpretation, although other people don't agree with it, but there are some historians who think that book one of Euclid's Elements is in fact a reverse undertaking, because it contains exactly what you need to prove the Pythagorean theorem and its converse, which are the last propositions. So if you agree with that, as I said, even when we have the whole text, the exegetics of it cannot agree on whether that's what Euclid was doing or not. But if we agree that that's what Hippocrates was doing, then certainly, yeah, he was a reverse mathematician. And if Euclid did that in book one, then he was a reverse geometer as well.
Thanks. And the second one concerned the interpretation of Pappus analysis. I know that there is a sort of debate about whether the Pappus analysis should be interpreted as a downward or upward movement.
Exactly.
Yeah. And for example, Comandino translate the text in the Pappus text regarding the analysis and synthesis, translate the analysis as a deduction, as a downward movement.
Yes.
What is your opinion about this debate and about the?
Well, to me, it seems from what he's saying is that you have to go upward in the discovery phase, and that you go downward once you're done with it. It is a certain sense you could say that, well, you start with a theorem, but you're not looking for if you look for consequences of the theorem is rather complex. The consequences would tend to be even more complex. So I don't see how that would work. So I'm thinking that it would have to be upward on the basis of experience of how do you do this? How do you work this out? So I personally think that that it is a case of a reverse thinking what he's telling us that we're doing.
Yeah. Thanks.
Any other questions?
No other questions? Okay, then I would like to thank Professor Pambuccian again for his lecture. And I remind everybody that the next lecture is the 28th of April after the Easter holidays, and it will start at 11. See you all then. Bye-bye.
Bye. Thank you.